I'm in SPSS and we're going to look at building a general linear model. I'd like to start off with a very simple model, and this is to explain the concepts, and then we can look at building a full model if you're keeping up. Now, to explain the simple model, I'm going to start with a graph. Now, we've already looked at doing scatter plots in regression where we have one variable plotted against another variable, such as cholesterol versus weight. And this time what I want to do is I want to colour by a third variable, so I want to include some group information. So I could choose either gender or ab fat. I'm going to just choose abdominal fat just because it gives us a nicer looking graph to discuss. So if I click OK, you can see what I get here is a scatter plot as I've seen before, but now we're colouring by a third group. So we can look at, within this relationship between weight and cholesterol, is there a different effect depending on the amount of abdominal fat that you have? And this is how we're building our general linear model. We're asking to see, if we've already accounted for one variable, what is the effect of another? And it looks like here that even inside this relationship of cholesterol increasing as weight increases, there is a higher increase in cholesterol for people with severe abdominal fat than there is for people with low abdominal fat. And so we're going to look at this with the model. To build the general linear model, we go to Analyze, General Linear Model. Make sure you don't choose the generalized linear model. This is a more advanced model, and we're interested in univariate, the first option. Our dependent variable is cholesterol. Now let's just keep the model simple, so I'm not going to put all of these variables in the model, although we can do that after. The fixed factors, these are any categorical variables that you have, and we're just going to look at ab fat. And a covariate is something which co-varies with the dependent variable, and this would be another continuous variable. So I am going to put weight into this one. Now by default, I believe that SPSS will build a full model with all interactions, and we just want the simplest model with the main effects. So we're going to go to Custom, select both of these, choose Main Effects, and then click Continue. In contrasts, we can choose just simple contrast for ab fat. We don't really need any plots at this stage. Now for any model that we build, we should be saving the residuals and taking a look at those. I won't do this for every single model we build just for time reasons, but I'll just do it for this first one to check that you are remembering to do it. So it's probably easiest if you choose your unstandardized predicted values. So this is the value of cholesterol we would predict for each person based on their weight and level of abdominal fat. Now this is not going to be a perfect prediction because our model is not going to be perfect. So there will be a little bit of error in every prediction, and these things left over are the residuals. And we're going to look at the standardized residuals, and this kind of just puts everything on the same scale so it's easier to look at. So pick that one there. Continue. Can't remember what's in options. Let me just have a look for display means. Yep, go on, show us the means for ab fat. Compare main effects. I don't know what that's going to do. Oh, it's going to put confidence intervals around it. We'll just have a look at it and we can ignore it if it's not being particularly helpful. Ignore bootstrapping. Now you will not need random factors in this subject, and you won't need any weighting. Okay, so every time you see a p-value or a significance, it means that a test was run. For the general linear model, you'll find that we have a test for each variable that we're interested in, and then there's a couple more. There's another one for the intercept, and this is not particularly important. It just means, are we starting off at 0 or are we starting somewhere else? So if we look back at the weight and cholesterol one, if I just double click this out and scale, if I set the scale to 0, and if I not that one, set this scale to 0. And the intercept means, is it crossing, is the model that we're fitting going to go through the 0 point when it comes through the y-axis here? So is this going to fit us multiple regression lines? Add fit line at subgroups, it will, nice. So what this is doing is essentially adding a separate regression line for each level of abdominal fat, and you can see that none of them are going to start at the 0 point, and that's all the intercept is telling us in that output, and we're just fitting straight lines here. And it does look like we do need an adjustment for each level of abdominal fat, which is essentially what the model is doing. So let's close out of that, and we can come down back to our analysis here. So the intercept, the null hypothesis for the intercept is that it is 0. We've got very strong evidence against that, and therefore we can assume that the intercept is not 0. Now normally you don't need to worry about this because no one is too concerned about predicting the cholesterol at the 0 mark, because there is no person which weighs 0, so this is not a prediction region for the model anyway. Abdominal fat. Now this is a variable which has 3 categories. The null hypothesis is that there is no difference in the means for the 3 categories. We have got very strong evidence against this, and therefore we conclude that there is a different effect of abdominal fat on cholesterol for each of the categories. Well, at least one of them is different, and then we can come down and look and see what those differences are in a minute. From the graph, we would expect that each level is different from the other, that with increasing abdominal fat we're getting increasing cholesterol. But it's possible that 2 of them would be the same and just 1 of them different. Weight. Now weight is a continuous variable, and so the null hypothesis here is that the slope of the line is 0, and we've got very strong evidence against that, and so there is a relationship between weight and what are we looking at? Cholesterol. So we've got very strong evidence that both abdominal fat and weight are important in predicting cholesterol levels. Our adjusted R-squared is 0.9, so we're explaining about 90% of the variation in the data with this model, which is really high, and it's mostly really high because it's fabricated data, it's not real data. So, abdominal fat, which is the easiest one to look at. This is probably the best one here, the estimated marginal means. So this is saying what is the average cholesterol for each of these levels of abdominal fat. And so with low abdominal fat we've got a level of 5.4. I can't remember how cholesterol's measured. I think it's milligrams per deciliter of something or other. I'm not a medical person, but you can look up how cholesterol is measured. And so we've got very low levels to very high levels on average for the different levels of abdominal fat. That's probably the best one to look at, that box there, and safe to ignore the pairwise comparisons. We can see that none of these confidence intervals overlap, and so we do have a significant difference between all of these groups. We've got more tests on cholesterol. So if we go back to our model, you can see that we've got 2 new variables here, our predicted variables. So we might call this, what should we call this? Simple model. If you run several models together, you're going to get lots of outputs for predicted and standardized predicted values and standardized residuals, and you'll lose track of which ones go with which model. So I'm just going to label these, and I may not output them for all models until we're finished. Simple model, standardized residuals. I might even change that to be predicted. Z residuals. The Z stands for standardized, if I haven't said that before. If you just took the unstandardized residuals, then that wouldn't have the Z on it. And what this does is it makes sure that all the residuals are centered around 0, which they should be anyway, but it scales them down so that they mostly lie between -3 and 3. And it means that you're able to compare residuals across models and also across the range of the values. So if we look at these, because we want to check that our residuals are normal, we can do a histogram of the standardized residuals. So this is the errors, all the bits left over. We're interested in checking that they are normal. And that's a little bit skewed to the right, but that looks okay. We could have put a curve over that actually. Let's do that. Yeah, so it's a little bit, we're missing, either we've got a couple of extra values on this side or we're missing some on this side. So it's not quite normal. We could do, and just wondering if it'll give me a normality test, a PP plot for the standardized residuals, test if it's a normal distribution. It's looking a little bit wiggly, but I'm going to accept it in this case. I know that with the full model the residuals do turn out to be normal. In this case there's a little bit of a problem with them. So you could, if this was as far as your model went and you ended up with residuals that were not quite normal, then you might need to add in that perhaps some further adjustment to the model was needed to account for these residuals. The other thing that we're interested in looking at, we can do with a scatter plot, and we want to see if, and this is the same as for regression, we want to see if the amount of variation in the error is the same for the whole range of the predicted values. So we're predicting values for cholesterol which go from 5 point something or other up to about 6.2, and we want to know, is there the same amount of error in the model across all areas of the predicted values. So we're putting the predicted values along the x-axis and the standardized residuals on the y-axis. And here's our zero line, and often it's worth adding that zero line in. It's a little bit frustrating that SPSS won't give you all of these diagnostic graphs just for you, because it's certainly a standard feature in Minitab, and so it'd be handy if it would just spit them out. So there doesn't seem to be any patterns here. If there was a curved relationship between weight and cholesterol, then we might see a curve come out in the residuals here, but I can't see any patterns there. So that's the simple model. What's the time? I'm going to stop there and I'll do a separate video on the more advanced model with interaction.